Hello everyone. Hope you are doing very well. Today, as you all know, that we are going to cover the theory part 6 of the chapter coordination compounds. So let's begin our today's topic, NCRT chapter 5 coordination compounds, theory part 6. And today we are going to cover the NCRT section 5.5.4. This is disclaimer. The objective of today's lecture. So after attending this lecture, you will be able to understand the nature of the bonding in coordination compounds in the crystal field theory. So according to the crystal field theory, how is the nature of bonding is going to be present in the coordination compounds? That is what you are going to understand today. So let's see the topics that we are going to cover according to the NCRT. The section 5.5.4, which is crystal field theory, that is CFT, right? And in this, we are going to cover today the first part of this, that the crystal field theory of the octahedral complexes. The other part of this section, which is crystal field theory of tetrahedral complexes, we are going to cover in our upcoming lecture. So today we are going to focus on this particular octahedral complexes and how this geometry of the complex, that is octahedral, is going to be like how the bonding in the octahedral complex is going to be there according to the crystal field theory CFT. So let's begin with our today's topic, subsection 5.5.4 crystal field theory, that is CFT. So there are some assumptions of the crystal field theory that you have to take while understanding this theory. First, that the crystal field theory, what is a crystal field theory? Which is it is an electrostatic model. So what does this states? That metal ligand bond in the complex as purely ionic, arising from the electrostatic interaction between the metal ion and the ligands. Until now, till the valence bond theory, we have covered that the metal ligand bond is a coordinate covalent bond, right? But in this theory, the crystal field theory, as this is an electrostatic model, that means it says that the bond between the metal and the ligand is as purely as ionic bond, and this is why this nature of the bond is arising between the metal and the ligand, due to the fact that electrostatic interaction is present between the metal ion, the central metal ion present in our complex, and the ligands which is approaching or which are approaching towards the metal ion. So ligand, let's see, we have different definitions under the crystal field theory for the ligand, which we assumed that we have a anionic ligands, which is considered as negative point charges. Anionic means negative charge. Anionic ligand means a negative point charges, okay, which are going to surround around the central metal ion or atom. Second, ligand is a type neutral ligands, in which it is considered as a point dipoles with the negative and oriented towards the metal. Okay, so neutral ligand means, neutral means having no charge, so it is considered as a dipole point. Okay, and its negative end is oriented towards the metal ion in the structure. For example, ammonia and water molecule. Ammonia is a neutral ligand, it doesn't have any charge. Similarly, the water molecule is also a neutral ligand, which is present there as a point dipole, in which its negative end, like in the H2O, if you see, negative end is O negative, like oxygen. Okay, so this oxygen or this negative end of the water molecule present as a neutral ligand is oriented towards the metal, which is going to be there in the complex, around which the water molecule is going to be present as a ligand, as a neutral ligand. So we also made one such assumptions of CFT as degeneracy of the d orbitals. Here assumption is that the d orbitals degenerate. Okay, what does that mean? In an isolated gaseous metal atom or ion, all the 5d orbitals, we know that the d orbital consists of 5 various energy spaces, right? So we can call them as the 5d orbitals, which is dxy, dyz, dxz, dx square minus y square, and dz square. Okay, so in an isolated gaseous metal atom or ion, all the 5d orbitals, these 5d orbitals are degenerate. That means they are having the same energy after the degeneration. Degeneracy would be maintained if the metal ion were surrounded by a spherically symmetrical field of negative charges. Okay, so what we are saying that degeneracy would be maintained. So the degeneracy of the d orbitals, okay, degeneracy of the d orbitals is maintained if our metal ion in the complex is surrounded by the spherically symmetrical field of the negative charges of the ligands negative charge, you can say, or the electrons. Okay, next is splitting of d orbitals, or you can say loss of degeneracy. So first of all, the degeneracy happens in like all the 5d orbitals. Okay, so basically in a free transition metal ion, the degeneracy in the d orbitals refers to equal energy levels of 5d orbitals. Okay, degeneracy is referring to the equal energy levels of the 5d orbitals. Okay, now in absence of the ligands, these 5d orbitals have same energy. Okay, which 5d orbital we just have seen, dxy, dyz, dxz, dx square minus y square, and dz square. They have same energy in absence of the ligand. Now the loss of degeneracy happens when the splitting of d orbitals happens or takes place. How? So in a real complex, negative field created by the ligands is asymmetrical. Okay, until the degeneracy of the d orbitals, there was the symmetrical spherical field generated by the ligands or the negative charge, right? But after the loss of the degeneracy, when we got a real complex, this negative field which was created by the ligand is become asymmetrical. Asymmetry causes the degeneracy of d orbitals to be lifted, and because of this asymmetry in this spherical symmetrical field that was created by the ligand, now this is asymmetrical, and this asymmetry is causing the degeneracy of the d orbitals to be lifted. Okay, which leads to their splitting into the different energy levels. Okay, so what does happen basically, when the degeneracy happens and you got the 5d orbitals of equal energy levels, then a symmetrical spherical field is created around the metal ion by the ligand, by the negative field. And when you got a real complex, the loss of degeneracy happens due to the splitting of d orbitals, because this symmetrical field is got asymmetrical, and when ligand approaches, it is going to interact with the d orbitals, and the ligand electron is going to repel the d orbital electron, due to which this energy difference happens, and the d orbitals is going to be split into two different energy levels. Now what is the splitting pattern of the d orbital? So if you observe, a specific pattern of this d orbital splitting is determined by the geometry or the nature of the crystal field, that is the arrangement of ligands around the metal ion. Okay, so how this splitting pattern is going to be, that is going to be determined by the nature or the geometry of crystal field. That is how the arrangement is going to be arrange itself around the metal ion. Okay, so how the arrangement of ligands is going to be around the metal ion, which decide the geometry of the specific complex, which is going to determine the d orbital splitting happening, or the specific pattern of the d orbital splitting happening or takes place in the complex. Okay, so the nature or the geometry of the crystal field, that means the arrangement of the ligands surround the metal ion, that is going to decide the d orbital specific pattern split. Now, let's talk about the first part under the crystal field theory, which is in the octahedral complexes. So, how you observe or how you see the crystal field theory in the octahedral complexes. So, for the octahedral complexes, the splitting pattern is distinct and plays a crucial role in determining their properties. Okay, how the d orbital is splitting, this pattern of the splitting is very different in the octahedral complex, and that is also going to play a very important role in determining the properties of that complex. So let's talk about the first part, that is the unperturbed d orbitals. What does that mean? So in an isolated gaseous metal ion, the 5d orbitals which we have talked about, the dxy, dxz, dyz, dx square minus y square, and the dz square, they all are degenerate. That means they are having the same energy. Okay, so in the isolated gaseous metal ion, the 5d orbitals are degenerate. That means they all have same energy, similar energy levels. So the second thing is approach of ligands in a spherical field. Now when this arrangement, or when this like stabilization of similar energy is going to be developed in the 5d orbitals, or you can say degeneracy when takes place in the 5d orbitals, then second step is that approach of the ligands in a spherical field. And when the spherical field built around the central metal ion, after what the approach of the ligands will happen in that spherical field. And the ligand approach means ligands are going to move towards the central metal ion to form the bond. Okay, so ligands are going to move towards the central metal ion. This is the ligand approach. Then hypothetical spherical field, the uniform spherically symmetrical electrostatic field is assumed. Okay, we assume that we have a hypothetical spherical symmetrical electrostatic field around the metal ion. Now energy increase happen. So when all the 5d orbitals is present in like degenerate manner, having the same energy, having the similar energy, and then when the ligand approach toward the spherical field, toward this uniform spherically symmetrical electrostatic field which was assumed, now these all 5d orbitals is going to increase its energy. Okay, so energy increase happens. Then the cause of increase, why the energy increased? Because when the ligand are approaching, so the repulsion between the metal d electrons and the ligand negative charge, or the ligand electrons richness. Okay, so why this is a there is a observance of the energy increase in the 5d orbitals, which was having the similar energy before, right now. But after the ligand approach in the hypothetical spherical field, all the 5d orbitals increase its energy. Why? Due to the repulsion between the metal d electrons, means electrons present in the d orbital, and the ligand negative charge, or the ligand electrons. These electron repulsion cause this increase of energy. Okay, so basically the difference in the repulsion, this electron repulsion is causing basically the splitting of d orbital. Okay, so degeneracy maintained, so d orbitals remain at the same energy level relative to each other. Okay, now what happens that the energy increased, okay, due to the ligand approach, due to why the energy increase, due to the repulsion between the electron and electron, between metal d electrons and the ligand electrons or negative charge. And degeneracy is maintained by the complex, so by the orbital, so d orbitals remain at the same energy level relative to each other. That means like relative to each other, the d orbitals are still remaining at the same energy level. Okay, so degeneracy, which is actually what is referring to the equal energy levels of 5d orbitals, degeneracy is maintained. Third step include the splitting in an octahedral field. Now when the electrons is approaching it is entering the hypothetical spherical field around the central metal ion, the energy is increasing, but still the degeneracy is maintained. Here the third step involves the splitting in an octahedral field. Now as the ligands come more close to the metals, because they are approaching towards the metal, right? So as ligands come more and more close to the metal ion, the d orbitals experience strong repulsion of the metal. So d orbitals of the metal is going to experience stronger repulsion and results in the splitting of d orbital, due to which the splitting of d orbitals happen. Okay, so ligands, when the ligands are approaching and they are going to interact with the metal d orbitals, the ligand electron repel the d orbital electron. Okay, and due to this stronger repulsion, as the ligands come close more and more to the metal, the d orbital of the metal is going to experience stronger repulsions, due to which the splitting of d orbitals happens. Okay, so difference in this repulsion is going to cause the splitting of d orbital into two sets of non-degenerate orbitals. Let's see that. So dx square minus y square, dz square orbitals, they are present as Eg, which set the phase ligands directly in the octahedral complexes, thus are raised in the energy. So what does that mean? So basically d orbitals with the lobes pointing along these axes, dx square minus y square and the dz square, will experience more repulsion and high energy compared to the d orbital with the lobes pointing between the axes, like present in the case of dxy, dyz and the dxz. Okay, so what we are saying that we have 5d orbitals having still the degeneracy maintained, right? But when the ligands come more closer in the approaching manner, when the ligand come more closer to the metal, the d orbital electron and the ligand electron repulsion increases, and the strong repulsion results in the splitting of the d orbitals, in which it is going to split into the 2d non-degenerate orbitals. Okay, non-degenerate means the difference of energy is going to be there between the orbitals, where we got this 2 orbital set referred as Eg set. The 2 orbitals are dx square minus y square and dz square. These 2 orbitals, which is referring in the Eg set, is going to face the ligands directly into the octahedral complex, and thus they are raised in the energy. Okay, so the lobes of these 2 orbitals, dx square minus y square and dz square, they are going to pointing along the axis. Okay, due to which they are going to experience more repulsion and higher energy difference. Okay, so they are raised in the energy as compared to the orbitals which are directed between the ligands, which includes dxy, dyz and dxz, and they are present as T2G set. Okay, so as I said that splitting of d orbitals happen between the two non-degenerate sets. One include Eg set, where 2 orbitals are there, dx square minus y square and dz square, and this is higher in energy because the lobes of these orbitals are going to be along these axes, which are going to due to which they are experiencing more repulsion and the high energy. So they are higher in energy compared to the T2G set, which include the orbitals dxy, dyz and dxz, which is directed between the ligands, okay, or between the axes. Okay, so the lobes of these dxy, dyz and dxz ligands orbitals are going to pointing between the axes, which is why they are going to experience less repulsion comparatively, and they are lowered in the energy comparatively with the Eg set. Now these energy changes are relative to the average d orbital energy in a spherical crystal field. So basically in the spherical crystal field there is a presence of average d orbital energy, and the energy which is changing, like whether it is raising for Eg and it is lowering for the T2G, these energy changes which is happening, they are relative to the average d orbital energy which is present in the spherical crystal field. So let's talk about the Eg set of orbitals first of all, because they are higher in energy and also facing higher repulsion. The Eg set of orbitals include the d orbital dx square minus y square and the dz square. Metal lobes lie directly along the Cartesian axis x, y and z. If you know the shape of these two orbitals dx square minus y square and dz square, then you know that in these two orbitals cases, the metal lobes, these orbital lobes are going to lie along the Cartesian axis, which are x, y and z in the 3D space. Okay, so dz square is along the z axis and dx square minus y square lobes is along the x and the y axis or Cartesian axis. Okay, ligands are positions directly along these axes. Now ligands, when approach towards the metal, they are also going to position along these axes, the Cartesian axis x, y and z. Okay, so they are also positioned directly along these axes, in which the Eg set of orbital or you can say dx square minus y square dz square lobes are lying directly. Okay, now what will happen when two lobes having the some negative charge or electrons, in the case of metal lobes, they are going to like present directly along the similar axis, okay, in the same axis. What will happen? Due to these positioning along the same axis, they will experience greater repulsion from the ligands. The metal lobes is going to experience the greater repulsion from the ligand negative charge or electrons, because there is electron repulsion happening. Okay, due to this greater repulsion, the energy is raised, energy increased. If you talk about the T2G set of orbitals, which are including dxy, dxz and dyz set of d orbitals, so in this case T2G set of orbital, metal lobes point between the Cartesian axis. Okay, here what is happening, the metal lobes of these d orbitals, they are going to point between the Cartesian axis. Like if you are taking x axis and y axis, then the lobe is going to point between the x and y axis, not along the axis, but at the 45 degree of from the axis. Okay, the metal lobes are present at the 45 degree of the axis. That means between the Cartesian axis they are going to be point towards. Now the ligands, when they are approaching towards the central metal and to form the bond, to form the complex, the ligands are positioned along the axis. Okay, their direction is going to be constant, that they are going to position themselves along the Cartesian axis, not in the case of T2G set of orbital, not directly at these lobes, because lobes are present between the Cartesian axis, but ligands are positions along the axis. Okay, so they are not directly at these metal lobes, the ligands, due to which they will experience lesser repulsion from the ligand. So metal lobes here in this case is going to feel or is going to experience lesser repulsion comparatively from the Eg set of orbitals from the ligands. Okay, so comparative to Eg, the ligands or these metal lobes are going to feel or going to experience lesser repulsion from the ligands, because there is the lobes of the ligands and the metal lobes are not directly on each other, but they are in the different direction. The metal lobes are between the Cartesian axis, meanwhile the ligands are positions along the axis. Okay, so the repulsion will be there between the electron present in the d orbital of the metal and the ligands, but the repulsion as compared to the Eg set will be lesser, due to which here in this case T2G set of orbital, the energy is lowered. Okay, remember we are studying this in the crystal field theory in the octahedral complexes. This is important to note. These all things which we are studying regarding the like splitting of the d orbital, it is present, or it is in the case of the octahedral complexes we are studying. Now you can see this diagram which is explaining everything we have just covered. So this is a figure explaining the d orbital splitting in an octahedral crystal field. You can see we have metal d orbitals here, okay, having the lower energy in the stable form, okay, and we are considering the three Cartesian axes, here the x-axis, here the z-axis, and here inside the plane. Okay, this dash line means this is inside the plane, which is y-axis, and this line x is bold line which is present and which is denoting outside of the plane, which is present as a x-axis. So 90-degree is the angle present between the two axes. Okay, now here we have a metal d orbital. So when metal is going to like have the 5 degenerate d orbitals and going to build a spherical symmetrical field around itself, and the ligands are going to approach in this field and form the bond with the metal and like arrange themselves around the metal in the octahedral geometry, and the complex will have going to be made. Okay, so we have a free metal ion where it consists of 5 degenerate d orbitals, the dx square minus y square, dz square, dxy, dxz, and dyz. Okay, now what will happen, the degeneracy is going to be still maintained, but the ligands are approaching towards the metal, okay, towards the metal spherical field. So average energy of the d orbitals in the spherical crystal field is going to be maintained still, but now what will happen, the energy is increased. Somehow the energy increased due to the ligand, because ligands are approaching towards this symmetrical spherical field present around the metal, right? So because ligands are approaching towards it, and they are is going to enter in this symmetrical spherical field, the average energy of the d orbital in the spherical crystal field is maintained, but the energy is going to be raised by some amount. Okay, now what will happen, when ligands comes more closer to the metal to form the bond with the metal in the octahedral manner, what will happen, the splitting of d orbitals occurs in the octahedral crystal field. Okay, in the octahedral crystal field, the splitting of d orbital happens. So the splitting happens, and the orbitals which distinguish, or they are going to separate between the EG and the D2G set. Why? Because the two orbitals, that is dx square minus y square and dz square, they are going to get higher energy because of the lobes placement and the ligand placement or position along the same axis, due to which the repulsion increases, and due to which the high energy caused. Okay, so dx square minus y square and dz square are going to be placed in this EG set having higher energy, and also the orbitals dxy, dxz, and dyz, they are going to be having lower energy comparatively to the EG set. So the d orbital is going to split between the EG and the T2G set. And why dxy, dxz, dyz are having lower energy comparative to EG? Because in these orbitals, the lobes of the metal is going to be positioned or present between the Cartesian axis, but the ligand is going to be positions itself along the axis. So repulsion is lesser comparatively, due to which the energy will be lesser, and the T2G will be placed in this manner as compared to the EG set. Okay, so this is happening, and you can see that this delta naught is representing the crystal field energy. Naught is this naught is basically representation for O, that is octahedral crystal field. Okay, so the d orbital average energy is rising by 3/5 delta naught to give us the EG set, and it is lowering by 2 by 5 delta naught or minus 2 by 5 delta naught to give us the T2G set of the non-degenerate d orbitals. Okay, so this is what this image is explaining. Now barycenter, okay, you can observe here we have written barycenter. What is barycenter? It is a dashed line in the middle which represents the average energy of the d orbital. So the dashed line present in the middle between the EG and the T2G set, this is representing the average energy of the d orbital, which is, you know, corresponding to this average energy of d orbital in the spherical crystal field, this. Okay, so when the energy is raised but not the bond has been formed, then we got the average energy of d orbitals, and when the ligands come more closer to the metal, the splitting of d orbitals happens. But here a dash line is present from this average energy of d orbital representation to the, like, the splitting of the d orbitals. This dash line is representing the barycenter, which is represent the average energy of the d orbital, which is express that total energy which is lowering of the T2G set equals the total energy which is raising of the EG set, ensuring that the barycenter remains constant. Okay, so this is the concept behind the barycenter. Let's see the energy. Let's talk about the energy difference. We represented by delta naught or 10 dq. So the energy difference between the lower energy T2G set and the higher energy EG set, this is called the octahedral crystal field splitting energy, that is CFSE, the short form. Octahedral crystal field splitting energy, CFSE, crystal field splitting energy. Okay, so the energy difference between the lower energy T2G set and the higher energy EG set is referred to this CFSE, octahedral CFSE, and it is denoted as delta naught or sometimes 10 dq, where dq is a unit of energy. Okay, dq is a representation for the unit of energy, and it can also be represented by delta naught, the CFSE or octahedral CFSE. This O is representing the octahedral. So how the energy's contribution is going to be there? So each electron which is going to be filled in the T2G set. So T2G set have three different orbitals, right? dxy, dxz and dyz. In these d orbitals, a pair of electron is going to be filled, right? So each electron in the T2G set stabilizes the complex by minus 0.4 or minus 2 by 5 delta naught amount of energy. Okay, so each electron present in the T2G set is going to stabilize the electron by this much amount of energy. Similarly, each electron in the EG set is going to be destabilize the complex by plus 0.6 or 3 by 5 of delta naught. Okay, so the energy difference between these sets EG and the T2G is called the crystal field splitting energy, CFSE. It is denoted by delta naught or 10 dq, where dq is the representation or unit of energy. Okay, and the magnitude and the pattern of splitting is basically dependent upon the geometry of the complex and the nature of the ligands. Okay, like how the ligands is going to be arranged themselves around the central metal ion, that means the geometry, and what is the nature of the ligand, that is going to be affect the magnitude and the pattern of the splitting happening. Okay, and as we have seen that the energy contribution will be in this manner, that in the T2G set each electron is going to stabilize the complex by this much of energy, that is minus 2 by 5 delta naught, and in the EG set each electron is going to destabilize the complex by positive 0.6 or 3 by 5 delta naught. We are saying here stabilize and destabilize because T2G set is having the lower energy. So if the electron is going to be filled in the T2G set, it is going to be stabilized by this much amount of energy. But if the electron is going to be filled in the EG set, that is going to be destabilize the complex because EG set is having higher energy. Higher energy means destabilization, right? Let's see the factors which affect the crystal field splitting, or you can say delta naught. First, field produced by the ligand. So strong field ligands, if we have strong field ligands, that will cause large splitting of the d orbitals. That means the delta naught will be larger. Okay, so the how the field is going to be produced by the ligand, that is going to be affect the uh, crystal field splitting, that is delta naught. So if we have strong field ligands, the ligands will going to cause the largest splitting between the d orbitals, that means a larger delta naught. Now if we have weak field ligands which are present in our complex, then the ligands will cause small splitting of the d orbitals and resulting in a smaller delta naught, smaller crystal field splitting. The splitting will be lesser. Second factor is charge on the metal ion. So in the central metal in the complex, the central metal ion present having some charge on it, right? So if the charge is higher, it is going to generally lead to stronger interactions and thus larger splitting between the d orbitals. Okay, and larger splitting means larger delta naught. So charge of the metal ion is also going to affect the crystal field splitting delta naught. Third is that spectrochemical series. What is spectrochemical series? The definition is that series where the ligands are arranged in the order of their increasing field strength. Okay, so how we are saying that this is a strong field ligand or this is a weak field ligand? This is the reason, the spectrochemical series. So it is a series where we arrange the ligands in the manner of their or in the order of their increasing field strength. Okay, how their field strength is increasing? One by one, ligand by ligand, we arrange the ligands in this manner, and the series we got is spectrochemical series. And what is the series? If you want to see, we have, this is the series, spectrochemical series, where I negative is the ligand which is having the lowest field strength, and carbonyl here in this series is representing the ligand having the strongest field strength. Okay, so weakest field strength to strongest field strength, we have arranged the ligands in the order of their increasing field strength. So iodide ion, bromide, SCN negative, chlorine negative, S2 negative, F negative, fluoride ion, OH negative, hydroxyl ion, C2O42 negative, C2O42 negative, H2O. H2O is like in the middle. Okay, you call the strong field ligand as strong field after the H2O, and you called ligand as weak field before the H2O. Okay, so all these from the iodide to carboxylate, C2O42 negative, we have weak field ligands. H2 is a neutral ligand, and then after H2O we have a strong field ligands like NCS negative, EDTA4 negative, NH3, EN, CN negative, and carbonyl. Okay, so these are the ligands which are weak, strong field ligands, and these are the ligands which are weak field ligands, and H2 is in middle, so it is a neutral ligand. How can you learn this series? Okay, so to learn this series, you can learn in this manner, that first the halogens came, right? In the weak field we have iodide, bromide, chloride, and fluoride, right? So halogens came. Then we have oxygen donor, you can say ligands like hydroxyl, C2O42 negative, and H2O. Okay, then we have nitrogen donor ligands like NCS negative, EDTA4 negative, ammonia. Then we have carbon donor ligands like EN, CN negative, and CO. Okay, so EN also comes in the nitrogen donor, CN negative and CO will come in the carbon donor. Okay, so this is the way in which you can learn. You can try to learn the series in this manner also. It will be easier. And what is the origin of this spectrochemical series? So this series is experimentally determined based on the absorption of light by the complexes containing different ligands. So we didn't put this series as it is from anywhere. We have done the experimental data, or we have done the experiments from which we got the experimental data. So the series is determined experimentally based on the absorption of the light by different complexes which contain different ligands. So we arrange then these ligands in the manner of the absorption of light. Okay. Mnemonic device in a table format for the spectrochemical series. So if you want to learn the mnemonics, the sentence will be: ice brings sweet, clear, salty, fresh, healthy calories. Water naturally energizing, nourishing, entertainment, creating comfort. Now what I'm saying, let's see. So let's see the table of mnemonics where this statement will or this sentence will be applicable for the format of spectrochemical series. So first come the iodide ligand, you can call it ice. Okay, ice. Then bromide, you can call it brinks. Then SCN negative, you can call it sweet. Then chloride, and that is, you can call it, mnemonic word for it is clear. Then S2 negative ligand, whose mnemonic word is salty. Then F negative ligand, whose mnemonic word is fresh. And then OH negative ligand, whose mnemonic word is healthy. Okay, so ice brings sweet, clear, salty, fresh, healthy. This is the order of the ligands in the spectrochemical series. First iodide came, then bromide, then SN negative, then chloride, then S2 negative, then fluoride, then hydroxyl negative. And then comes in the order C2O42 negative, having calories as a mnemonic word. Then H2O represents for a water word. Then NCS negative, which is naturally, you can call it as an EDTA4 negative, you can call it as energizing. Ammonia, you can call it as nourishing. EN, you can call it as entertaining. CN negative, you can call it as creating. And CO, you can call it as comfort. So this is the mnemonics to learn the spectrochemical series order. Okay, from lowest to the highest field ligand. Let's talk about the electronic configuration in the octahedral complexes. So general rule for the first electrons. So if we are having D1, D2 or either D3, then what is the general rule for these electrons filling? For a single d electron like D1, only in the d orbital only one electron is going to occupying. So for a single d electron, it occupies one of the lower energy T2g orbital. So if we are only here for filling of the single d electron, the d orbital, it is going to choose in the between the lower and the higher set of orbital, it is going to choose the lower energy T2g orbital to fill. So for D2 and D3, the coordination, and for D2 and D3 coordination entities in which the electron filling is for the D2 or the D3 configuration, the electrons are going to occupy the T2g orbital singly, following the Hund's rule. Okay, Hund's rule says that each orbital should be filled singly first of all, and then when the half filled happen or half filled configuration takes place, then the pairing should start. So in the T2g orbital, we have 3d orbitals present, right? dxy, dyz, and dxz, right? So in each orbital, one pair of electron can be filled in the high spin and the lower spin, right? So for the D1 configuration, it is going to be filled in the lower energy T2g orbital. If the configuration is D2 and D3, the electrons is going to occupy still the T2g orbital energy. Like each d orbital is going to filled by one unpaired electron, like in the singly format, following the Hund's rule. Now, how the electron distribution will be for the D4 configuration? This is a crucial case. Why? D4 means 4 electrons, but we have only 3 orbitals in the T2g. Okay, so 3 like singly paired can be filled in the T2g, lower energy T2g orbital. 3 singly paired electron can be filled into the lower energy T2 orbital. Okay, but when comes the fourth electron, there will be 2 cases. Either the T2g orbital will start to pair up, okay, with the filling of the fourth orbital or fourth electron, or that fourth electron will go in the EG higher energy orbital for in the single occupied orbital manner. Okay, understand? Okay, so two possible patterns for the D4 configuration will be there of electron distribution depending on the competition between the two energy factors. Now, what is those? First is crystal field splitting energy, that is delta naught. So the energy difference between the EG and the T2G set of orbitals, which is saying as the crystal field splitting energy, which is a energy factor on which the competition of the filling of fourth electron is going to depend between the higher or the lower energy orbitals T2G and EG. Second factor is pairing energy, represents by P. So this is the energy which is required to pair the electrons within a single orbital. Like if fourth electron is want to filled into the T2G orbital only after the pairing up with the first d orbital in the T2G orbitals, that means the pairing energy is going to be required in the T2G orbitals to pair the electrons within a single orbital, right? So the crystal field splitting energy CFSE, denoted by delta naught, and the pairing energy, that is P, these are going to be the two energy factors which is going to determine that how the fourth electron in the D4 configuration is going to be filled, is going to be distributed among the two lower and the higher energy orbitals. Let's see the filling of the electrons for D4 configuration. You can see in this diagram representing the D4 electronic configuration with the high spin. What does that mean? Basically, high spin complex is formed. That means there is a weak field ligand present. Weak field ligand, what it will cause? We have studied that weak field ligand cause no pairing of electrons, right? So if there is unpaired electron present, they are not going to be pairing up, or they are not going to be paired up due to the presence of weak field ligands. Then we obtain a high spin complex. What is the condition of getting a high spin complex? First is weak field ligands presence. Then second is that if your CFSE, that is delta naught, is lesser than the pairing energy, that means pairing energy is more, that means crystal field splitting is smaller than the pairing energy. Okay, the crystal field splitting energy is smaller than the pairing energy. This is the condition. So if this is the case, then electronic configuration will be that fourth electron enters one of the higher energy EG orbital. Okay, in this case, when the delta naught is lesser than P, the pairing energy, then the fourth electron in the D4 configuration, 3 electrons are already filled in the T2G orbital. Okay, in the dxy, dxz and dyz, 3 electrons have already been singly occupied each of the orbital. Now the fourth electron, if the delta naught is less than the pairing energy, if the crystal field splitting is smaller than the pairing energy, the fourth electron is going to enter one of the EG orbital, which is here in case dz square. Now this is resulting into the configuration of T2G3, because in the T2G we have 3 electrons, EG1 because in the EG we have until now 1 electron. Okay. What is the ligand type? So ligands that cause this high spin complex is known as, or are known as, weak field ligands. Due to the weak field ligands presence, the pairing energy is going to be greater than the splitting crystal field splitting energy, due to which the fourth electron is going to be occupied into the higher energy EG orbital. Okay, so complex type here will be, the complex are termed as high spin complexes because the electrons prefer to occupy the separate orbitals before the pairing up with another orbital. Okay, they prefer to go into the another orbital then to go in the pairing with some other orbital. Okay, so the complex type is, in this case, is high spin complexes, which forms due to the presence of the weak field ligand into it, which cause the electron filling into the higher energy level, that is EG orbitals, due to which we obtain this resulting configuration of T2G3 EG1, and the energy difference between these T2G and EG is smaller, so the delta naught is smaller, due to which the electrons will jump into this higher energy EG orbital and gets singly occupied the dz square orbital in the EG set. Okay, and formation of high spin complex forms, and the condition is delta naught, that is smaller crystal field splitting than the pairing energy. Let's take the another case of the filling of electron for D4 configuration, which is including low spin complexes formation, that is strong field ligands present, right? This is the diagram showing the D4 configuration with the low spin. Low spin means that there will be larger crystal field splitting, that is delta naught will be larger than the pairing energy. So the electron, that is fourth electron, is going to be undergoing the pairing in the same energy level, like in the same T2G orbitals, and not jump into the higher EG orbital. So the condition for low spin complexes are that delta naught is greater than the P. That means crystal field splitting is larger than the pairing energy. Electronic configuration, so it becomes more energetically favorable for the fourth electron to occupy a T2G orbital and pair up, because there is a delta naught is larger. Delta naught is larger means the fourth electron, it is energetically favorable that the fourth electron will occupy the same T2G orbital and pair up with the existing electron present in a single pair, right? So it will undergo the pairing and doesn't move into the higher energy EG set. The resulting configuration from this action will be T2G4 and EG0. T2G4 means in the T2G set we have 4 electrons filled, in which 2 are paired, and EG0, EG got no electrons. The ligand type here is strong field ligands that produce this effect. Okay, strong field ligand cause the pairing of the electrons, right? Remember, we have studied. So crystal field theory even describe this fact, that why the strong field ligands is causing the pairing of the electrons. So the ligand type in the low spin complex is strong field ligand presence. The complex type we got is low spin complexes, because the electrons pair up in the lower energy orbital here, and this is the favorable, energetically favorable condition for those. Okay, so this is the diagram showing that there is a larger energy increase. So larger crystal field splitting energy is present between the two sets EG and the T2G. That's why the fourth electron which is going to come is undergoing the pairing in the same lower energy orbital, and causing and giving us the resulting configuration T2G4 EG0. And this happens and form a low spin complex where the delta naught is greater than P, and there is a strong field ligand present in the complex. Let's see the electronic configuration in octahedral complexes. So for the D5, D6 and D7, the D4 case is the crucial one, because that is going to decide either the fourth electron is going to be undergoing the pairing, or it is going to be singly present in the singly occupied orbital in the higher energy set. So for D5, D6 and D7 octahedral complexes, both high spin where the pairing energy is more than the crystal field splitting, and the low spin where the crystal field splitting is more than pairing energy, configurations are possible. Okay, D5, D6, D7, both the configuration high spin and low spin are possible, resulting in varying number of unpaired electrons. What if high spin configuration is there? So for D5, the high spin configuration will be T2G3 EG2. Okay, that means 5 unpaired electrons we are going to get. And for the D6, in the high spin configuration, we got T2G4 EG2, that is 4 unpaired electron. Third case is for D7, where we got T2G5 EG2, that is 3 unpaired electrons. So we prefer here the firstly singly occupy the orbitals, and then pairing will happen in both the cases, the higher energy EG and the lower energy T2G orbitals. Okay, in the high spin configuration we prefer the unpaired electrons more, then the pairing will happen. Okay, first of all, unpaired electrons is going to be filled in both the sets, and then the pairing will start. Okay, and according to that we got different number of unpaired electron. For the low spin configuration, we prefer the pairing more. So for the D5, we got T2G5EG0, that is a configuration, that is we are going to get 1 unpaired electron. For D6, we got T2G6EG0 configuration, that means 0 unpaired electron will be there, that is no unpaired electron. For D7, because we are getting T2G6, that means every orbital is filled in the T2G6, so 1 electron will go into the EG orbital. So T2G6 EG1, that means 1 unpaired electron will going to be there for D7 configuration in the case of low spin. Now for the D8, D9 and D10, the octahedral complexes, only 1 electron configuration is typically observed. What is that? It is D26EG2, because 2G is going to occupy, T2G is going to occupy 6 electrons and EG is going to occupy 2 electrons, and we got 2 unpaired electrons. For D9, we got T2G6 EG3, that is 1 unpaired electron, and for the D10, we got T2G6 EG4, that is 0 unpaired electron and no space for any extra electron, because D10 is fully filled, right? Max electron that can be filled in the d orbital is 10. So in the D10 configuration, this is for D8, D9 and D10, this is typically only the one configuration that is observed generally, where we got 2 unpaired in D8, 1 unpaired electron in D9 and 0 unpaired electron in D10 configuration. Crystal field splitting energy. Now if we explain the CFSE, and according to this diagram which we have already seen, right? So this is a d orbital splitting happening in an octahedral crystal field, right? So the definition, if you want to provide for CFSE, the energy difference between the actual d orbital energy level in a complex and the energy level of d orbitals in a spherically ligand field, that is that energy difference, and it is termed as crystal field stabilization energy. Okay, so energy difference between actual d orbital energy level in a complex and the energy level of d orbitals in spherical or isotropic ligand field. So this energy difference between these two conditions of the d orbital is going to termed as the crystal field stabilization energy. How can you calculate the CFSE? This include this formula. CFSE is going to be equals to minus 2 by 5 n T2G plus 3 by 5 n EG. We closed it into the brackets, multiplied by delta naught, which is the crystal field splitting energy magnitude, plus m times p. Here the n here is representing the number of electrons which is going to occupy the minus 2 by 5, that is T2G orbital, and 3 by 5 n, that is the number of electrons occupying EG orbital. Okay, so n is representing the number of electrons, delta naught is representing the crystal field splitting energy for the octahedral complexes. This O in the subscript is representing the octahedral, and m here is representing the number of pair of electrons in the splitted d orbitals minus the number of pair of electron in the degenerate d orbitals. Okay, so m is representing this difference of the pair of the electrons, so number of pair of electrons in the splitted d orbitals minus number of pair of electron in the degenerate d orbital. Okay, like in the initial case and after the splitting, what is the number of pair of electrons which we are getting? So that difference is the m, and p is our pairing energy. Okay, so this is the formula you can use for the calculation of crystal field stabilization energy. Let's see the example of CFSE calculation in the octahedral geometry with strong field ligand. So for the cobalt plus 3, that means it is having D6 configuration. So for the cobalt plus 3 ion, Cobalt plus 3 having d6 configuration, you can arrange that in a 3D orbital as in this manner, where we are getting 4 number of unpaired electrons and 1 paired electron. Okay, so this is CO3 positive in the spherical field. Now it is going to split into two energy levels, Eg and the T2G, higher energy and the lower energy. Okay, and the energy difference between them is representing by the delta naught, where the Eg is hiring its energy by 3 by 5 delta naught, and T2G is lowering its energy by minus 2 by 5 delta naught. So this figure is representing the crystal field splitting energy splitting diagram of cobalt 3 positive of octahedral complex. So for the cobalt, we know the atomic number is 27. Okay. So for cobalt 3 positive, we are considering here a complex where the cobalt is present in the plus 3 charge, having the d6 configuration. Cobalt is having that atomic number 27. So electronic configuration for cobalt plus 3 is going to be argon 3d6 after the donation of 3 number of outermost electron from it. The diagram explanation. So electronic configuration for cobalt plus 3 is going to be T2G6 and Eg0. So in the T2G, we got all the 6 electrons, all are paired, and the Eg, we got like no electron into it. So 0 unpaired electron in the D6 configuration, and T2G6. That means 3 paired electrons in the T2G set. Okay. This is a condition of low spin. Okay. Now for a CFSE calculation in octahedral geometry with the strong field ligand. So for the strong field ligand, if you are having a strong field ligand, what will happen? This is the CFSE splitting diagram for cobalt 3 positive of octahedral complex we just have seen, right? Now the calculation of CFSE is going to be there, which is equals to minus 2 by 5 n T2G plus 3 by 5 n Eg, and whole multiplication with the delta naught plus m times P. This is the formula which we have seen for the calculation of CFSE. Number of electrons here will be 6. In the T2G, we have 6. In the Eg, we have 0. Right? Because n are different in this formula. With the T2G, it is T2G electrons. With the Eg, it is n electrons. With the Eg, it is Eg electrons. In the Eg, we have no electrons, so n will be 0. With the T2G, we have 6 electrons, so n for T2G is 6. Number of extra pair electrons in the split orbitals. So we are going to determine the m. So here we are going to get 2 extra paired electrons, 2 set of paired electrons in the T2G as compared to this 3D like orbital in the spherical field for cobalt 3 positive. Right, here we are having only 1 paired electron set, but here in the T2G we got 3 paired electron. That means the difference between the pairing of the electrons in this 3D orbital in the spherical field and in the T2G orbital is 2. So 3 minus 1 is 2. Okay. So CFSE will be, we put simply the numbers. So minus 2 by 5 multiplied by n for T2G, which is 6, plus 3 by 5 multiplied by the n for Eg, which is 0, plus m is 2, so 2 times P. So it will be minus 2.4 delta naught plus 2P. This is the CFSE for this D6 configuration of the cobalt 3 plus of octahedral complex. So this is how you can calculate the CFSE for a particular octahedral complex. So CFSE of octahedral complex, where now we have going to see the table for the octahedral complexes with their crystal field splitting energies. So each having different d electronic configuration, and if they are having weak field, that means high spin configuration, then what will be the configuration of weak field high spin, and what will be their CFSE calculation for the weak field, and if the strong field is there for the low spin configuration, what will be the configuration, and then their corresponding CFSE, what it will be for the strong field. So you can see for the D1, we have T2G1EG0, for which the CFSE in the weak field is minus 0.4 delta naught. And for the strong field, T2G1EG0 is the configuration for which CFSE is minus 0.4 delta naught. Similarly, if you observe the change, we have for the D5, the weak field configuration is T2G3EG2. Every higher and the lower energy orbital is going to occupy it singly by the electrons, right? For it, the CFSE is 0. But if you are considering the strong field and the configuration is T2G5EG0, that means every electron is occupying the lower energy orbital T2G, then the CFSE will be minus 2.0 delta naught, right? Similarly, the change you can observe in the D4 and D6 and D7 configuration in the weak and the high spin, or you can say in the weak and the strong field, right? So from weak field minus 0.6 delta naught to in the strong field minus 1.6 delta naught. Similarly, 0 to minus 2.0 delta naught, minus 0.4 delta naught to minus 2.4 delta naught. Similarly, minus 0.8 delta naught to minus 1.8 delta naught. That means the CFSE is becoming more and more negative when it is moving from weak field to the strong field. The other values are similar in both the cases or the other configurations in the octahedral complex. Okay, so this is the table which is representing the different case for the configuration and for the CFSE calculation with different d electronic configuration of the octahedral complexes. Okay, thank you so much. That's all for today's chemistry session. Thank you.